Yeah, you can start your presentation.
Okay, thank you. So
Thank you.
you can see my slides now, right?
Yes, we can see us.
Nice, thank you. Hello, everyone. It's I'm very happy to have the opportunity to share my research progress recently. My name is Xiangming Xu. I'm from Professor Wilson Artsrift Group, and my current research is focused on the electronic thin film fabrication and the relevant circuits. So the topic I'm going to give is high quality 2D films preparation method for the large area integrated circuit. So I'm going to report three parts. One part is for 2D semiconductor thin film fabrication, especially focus on the moly-sulfide thin film preparation. And then I'm going to talk about the metallic MXene thin film preparation. And then after this, I'm going to talk MOF-based ionic dielectric thin film, of them for the especially for transistor. So first of all, semiconductor 2D material is a very important research objective currently because it has a very promising result. As we can see, since silicon-based transistor technology is going to reach the physical limit. So what is the physical limit? It means the channel length between the source and drain is close to 5 nanometer, then the transistor will not working properly. We cannot really turn on or turn off the drift current from source to drain if the channel is such a short length because of tunneling electron tunneling effect, also the short channel effect. So this is the silicon limitation. So that's why people thinking that maybe moly-sulfide is the best is one of the very promising candidate because it has very little short channel effect, and the thickness of moly-sulfide can reach to less than 1 nanometer. And also from this, let me use the leader pen. Leader point. From this graph, we can see that another advantage of 2D semiconductor is silicon. We can also reduce the thickness of silicon to further to minimize the short channel effect. But the thing is, if we reduce the thickness of silicon channel to less than 1 nanometer, we can see the mobility is greatly degraded. But for the 2D material, they can have a relatively higher field effect mobility, even with the thickness of less than 1 nanometer. So that's why it's a very it's getting a great interest in the relevant research community. But the thing is, currently most of the 2D material, they were born with a very small flake size, either by the exfoliation, mechanical exfoliation, or by CVD growth. So that's okay for the research purpose. But if we want to scale up the application, it will be a big problem. We cannot really use the single flake to make a industrial product. So that's why we need to enlarge the flake size by either growth or the other method. Currently, most of the growth method is based on the CVD process. CVD currently can not only grow the single flake. Single flake can reach to more than 100 micron, or even sub millimeter size, but that's also not big enough. But still, some of the group, they focus on the wafer scale growth. Since 2014, the people start trying to enlarge the 2D material thin size, and until now, there's already many CVD growth of 2D moly-sulfide coming. Since 2014 to 2018, we can see the size is keep increasing, but they all face a common problem. The thin film is not single crystal. The orientation of the grains is not mono-oriented, and also so it's rich of grain boundary defects. But of course, recently there's some paper coming. They publish in very big journal like Nature. They realized the mono-oriented growth, but still we all know that CVD growth is not stable. The repeatability and also the island, the multi-layer island cannot be avoided. So I'm thinking to use, so in our group, we are thinking different strategy, maybe two-step process. But if we review the reported two-step process literatures, we found that two-step process can usually have some advantage, which is predefine. It can predefine the thickness. First of all, let me introduce the two-step growth process. It means firstly, we prepare some metal-based precursor thin films, and then we do soft revision. So first is prepare the oxide, the precursor film, and then the second step is do conversion, chemical conversion. So it can predefine the thickness during the precursor thin film preparation process. Also, the precursor thin film can be the wafer size can also be predefined, so that finally our 2D film also can be defined. But currently we found that most of these two-step process give the 2D semiconductor very worse, relatively worse electrical performance. The reason is the crystalline structure is it's much even worse than the CVD polycrystalline film, because the grain boundary is much high. Grain boundary intensity is much higher. So we try to figure out what is the reason why two-step process cannot give a higher quality 2D semiconductor films. We are thinking we found that all these precursor film, they have amorphous structure. So it means the previous literatures, they prepare the precursor film, but they don't care the precursor film quality, especially the crystal quality. So I think so that's why we think more on these precursor quality things. So here is our process. We are thinking if we can prepare a high quality precursor by epitaxial growth, like this, we found that moly oxide can be a very good precursor for moly sulfide, because it can be epitaxially grown on C-cut sulfide substrate. As we know that C-cut sulfide substrate is already be used in the industry. So it means if we can also grow the high quality moly oxide precursor on C-cut sulfide substrate, and then if we get high quality moly sulfide, it means the industrial compatibility will be easy to reach. So this is our schematic. So first so how we prepare the moly oxide precursor? By this way, post laser deposition process. Before we do the deposition, we do a calculation and found that moly oxide has a lattice mismatch with a C-cut sulfide substrate, which is very small, no more than 2%. So theoretically, moly oxide can be grown epitaxially on C-cut sulfide substrate. And also why we choose post laser deposition to do the epitaxial growth, because post laser deposition is a powerful tool to grow oxide, especially epitaxial oxide. And also it can control the growth thickness, the thin film thickness, through the atomic thin layer by layer method. So that's and finally we achieved it. We by optimize the growth parameters in the PLD, we really realized the moly oxide epitaxial growth. We confirm its epitaxial structure, which is also mono-oriented structure by XRD. We can say from this 2 theta scan, in the outer plane lattice orientation, they only have 200 lattice plan, so it means it's really mono-oriented along the out-of-plane direction. From the phi scan, we can see 6-fold symmetry of this 011 peak, 011 lattice plane peak. So it means in plane direction, the architectural precursor is also mono-oriented. So this can double confirm that our moly oxide is very good in terms of the orientation, and it is really high quality. So if we do the conversion, finally we got the moly sulfide. We found that we also confirmed its mono-oriented feature by XRD. 2-theta scan showing us 2-theta scan showing us here. Only 002 lattice plan is showing in moly sulfide film, and also the phi scan showing the in-plane lattice lattice plan is also mono-oriented. So it means from epitaxial moly oxide, we can really get mono-oriented moly sulfide thin film. We further confirm by selected area different pattern in the TEM. So first of all, if we didn't prepare the high quality epitaxial moly oxide as the precursor, if we just use the normal amorphous moly oxide as the precursor, and then we convert into moly sulfide, we confirm that this moly sulfide is really polycrystalline structure. Here is the selected area diffraction pattern. It's ring-like. Ring-like means it's really polycrystalline structure. If the moly sulfide is from epitaxial moly oxide, high quality precursor, the moly sulfide is really a quasi-single crystalline structure. We can see we select many different areas, and they are all in the same orientation direction and the single-like crystalline patterning. Why we say it's quasi? Because we see the point is not really perfect rounded point. It's just an elongated point. So we are thinking maybe still some some like a tiny misorientation still exists. So we compared this quasi-single crystalline QSC moly sulfide electrical performance with the poly moly sulfide electrical performance by making a top-gated transistor. We found that the QSC moly sulfide has a much higher mobility than the polycrystalline moly sulfide. And also on-off ratio, the quasi-single crystalline structure is also much better. So after engineering the orientation, actually we still face a problem that time. That time I finished this project around the end of in the end of 2018. We have another problem. Through our process, we cannot really achieve the monolayer. Monolayer is highly attractive because it's really less than 1 nanometer, and it has many optoelectronic properties. So my next project is just focus on the monolayer growth use our epitaxial phase conversion process. This challenge is also common in the traditional two-step process. Actually, if we review all the previous literature, we found that the traditional two-step process has never been reported in grown monolayer, continuous monolayer film, because usually it can be, if we make the precursor thin film ultra thin, it will result in isolated flakes of moly sulfide. So we want to overcome this challenge by our own process. So here we found that we can minimize. We use our ultra thin, which is less than 1 nanometer moly oxide thin film, and by combination, by combine the gas flow engineering, especially we try to minimize the influence of gas flow on the surface separation. We really achieved a much better uniformity. As we can see, if the precursor film is parallel to the gas flow, it means the gas flow can really flow through the surface of the wafer. The thin film is not uniform. We can easily check by eyes. If the moly oxide is faced to the gas flow, it means the gas flow just directly go on the surface of the wafer, it's also not uniform. But if we minimize the gas flow by back to the gas flow for the surface of molybdenum oxide, we can really achieve very uniform thin film on the wafer. We confirm the uniformity by Raman and also PL, and we confirm the layer thickness, the monolayer feature. Usually, monolayer has a much higher PL intensity, which we confirm here. And also, we do many patterning, and we found that they are all in a very nice patterning. They are all continuous and free of multi-layer island. Of course, we have more patterning, which is in large area, but I didn't show in here. And also, the other advantage here is we can engineer the monolayer film structures. I mean, especially the chemical ratios. I think this cannot be really achieved in the CVD because the CVD growth of monolayer film, they have very small window to grow the uniform film. If you vibrate any of the growth parameters, the uniformity will be destroyed. But here we don't have this kind of concern. We can use many different saturation temperatures from 500 to 100, and the chemical the stoichiometry ratio can be well engineered so that the electron density can also be engineered. Also, the relevant PL physical, I mean, especially optical electronic properties. I will not give one detailed explanation, but I just want to show that this is the one of the advantage to use our epitaxial phase conversion, because we can really engineer the monolayer film without worry the uniformity be destroyed. Also, the monolayer film, we get another surprising result. The mobility is reached to more than 20 in average, and also a very good on-off ratio. So this is somehow similar to the single flake property. Another phenomenon we also figured out in the thicker film. We found that if we increase the molybdenum oxide precursor thickness more than around 5 nanometer, we found that we lose the orientation, as we can see here. After converting the molybdenum oxide into molybdenum sulfide, if the thickness more than 4.5 nanometer, it's no more a single crystal-like patterning, but it's also not it's somehow also different, a little different to the polycrystalline structure. We can still see there's some preferred orientation because of some area they are really highly, the point is showing. So it means there's a heavy texture in the thicker molybdenum sulfide if we use our epitaxial phase conversion process. So we were thinking that time maybe the reason is for the thicker epitaxial precursor film, they have somehow more defects such as dislocation. Actually, this is common if you are in the area of epitaxial growth. If we increase the thickness, the dislocation defects will be increased. It will be sure. It will be very obvious. So we are thinking if we have defects, we just think to minimize the defects, but it's not that simple, because even though here we say it's thicker, but it's also very thin. It's just 5 to 10 nanometer. If we do the annealing, directly annealing on this still very thin film, you will see this kind of phenomena. The very smooth surface will become rough. If we do the annealing in a very high temperature, like 900 degrees, it will be no more thin film. It will be isolated grains. So this is not favorable if we want to get the molybdenum sulfide continuous film through the conversion. So we developed another process, which is collab process. This is short name. The full name is capping layer annealing process. So we are thinking, if we want to enhance the quality without sacrifice the flat surface, we can put a capping layer on the surface so that the surface mass transfer will be minimized. If this surface mass transfer be minimized, it means the surface flatness can be well maintained. And after annealing, the thin film will be really with a high quality and also good surface. So here is the result of annealing of the precursor. This is our pristine. Pristine means as green moly oxide film, just after the growth of PLD. It's very thick. It's very small surface. Roughness just around 0.16. And if we do direct annealing at 900, you see the isolated grains. It's no more. It's not thin film anymore. So we don't like this because this cannot really give us continuous film. So we after using collab process we developed, we found the surface is still continuous even though a little roughness increase, but this is still acceptable for achieving the continuous thicker molysulfide film. This rocking curve showing us that capping layer annealing can really reduce the 4 ways of the half maximum of the rocking curve peak. So it means the quality is really enhanced. So this is the whole process. How we really the whole process. I show two comparison. One is if we do direct sulfurization, it will showing this kind of heavy textured near ring-like structure. If we use the capping layer annealing process and then do sulfurization, we will get the selected area different pattern like this. It's a perfect single crystal-like pattern. Three different direction showing three different area for the SAED characterization. They are all showing the same orientation. So it means we really minimized the texture in the molysulfide film and also control the thicker multi-layer molysulfide thin film orientation. Also, we compared the textured one and the single textured molysulfide and the single crystal molysulfide. Of course, single crystal has a relatively higher mobility, better performance, but the thicker film is somehow the performance is not as good. It's a little worse than the thinner one. This is the reason is coming from our epitaxial phase conversion, because each conversion process, it means the exchange, the sulfur oxygen exchange, the sulfur oxygen exchange is not as efficient as the thinner one. So the sulfur oxygen exchange defects will be much higher in the thicker film. So this is our explanation. Also, our wafer scale molysulfide film can be transferred on the a rigid and flexible substrate for different electronic application. So this is the conclusion. So we get monolayer film. We also control we can also control the mono orientation. Also very good performance. It's showing some advantage in control the, especially achieve the fill. This we can see. If in CVD we cannot avoid the fill layer island, but in our process we have no this concern. And also we have a bigger annealing window. So we are thinking the epitaxial phase conversion process can make very good quality molysulfide. Why not we can use this one to make the other 2D materials or even not 2D materials. So in total we can have like but for binary oxide compound we can have 165. For ternary, we can have like even more than 2,000 compound. So I think if we use epitaxial phase conversion, we can really have a very big space to explore. So after that, we do a deeper investigation on the multi-layer film. We found that in multi-layer film, we have a very interesting phenomenon, which is lattice orientation heredity. So how we figure out this phenomena? It's like this. So first we get the mono-oriented epitaxial molysulfide. We transfer from the single crystalline substrate to the amorphous surface, and then we do the conversion. Surprisingly, we found that this thin film converted from molysulfide, they still maintain the mono-oriented feature. So this is the real sample, molysulfide transferred on the quartz glass wafer. And then I cut into two pieces. One is converted into molynitride, another is converted into molycarbide. And we can convert very thin molysulfide into even around 1.5 nanometer molynitride. We can see this XRD is showing molysulfide on the quartz glass surface. They still have the mono-oriented feature along the in-plane direction and also the out-of-plane direction. After conversion, molynitride also same. They have also mono-oriented in-plane mono-oriented feature in the in-plane direction and also out-of-plane direction. Same to molynitride, molycarbide. So so we're thinking this phenomena. What is how can we use this phenomena? Finally we found that if we can, we do the literature investigation, we found that all the epitaxial growths, they are on the single crystalline substrate. So use the lattice orientation heredity phenomena, we can really achieve a high quality mono-oriented thin film on the non-single crystalline substrate, such as glass, amorphous substrate, and the polycrystalline substrate. So especially, recently the gallium nitride is a very popular material in the advanced semiconductor industry. And so we are thinking if we use our molynitride as a seeding layer on the surface of glass, and then we can achieve gallium nitride with also a mono-oriented feature. Here is our demonstration experimentally. We grow the gallium nitride on this molynitride surface by MBE, molecular epitaxy, molecular beam epitaxy. So they have the mono-oriented feature along the out-of-plane direction and also in the in-plane direction. So it means we really demonstrate that use our lattice orientation heredity, we can really achieve mono-oriented thin film on the non-crystalline substrate. So this is just initial demonstration. So it means we have a big space to further optimize the quality. Most probably, we can even achieve a higher quality reach to the thin film on the single crystalline substrate. So the above is for the investigation of molysulfide thin film preparation. In our group, we also did a lot of research on MXene things, but MXene, most of previous MXene research is for the application of energy storage and catalyst and seawater salination things. So most of these research, they are in the chemistry direction or maybe bio direction. So the research of using MXene in the electronics, especially thin film electronic direction, is much less. So that's why we want to see if MXene can really make a big role in this field. But if we really want to achieve this goal, we need to first prepare a good film. So my research is initially focused on MXene TS3C2. Titanium carbide thin film preparation process. Actually, MXene thin film preparation can be easily done by spray coating. Well, our demonstration, our exploration here is not just the thin film preparation. It's just to confirm if this thin film can be compatible in the nanofabrication process. So we did this. So first we spray coated MXene on the glass surface. So this magazine, of course, is also layered structure. This is the crystal model of the titanium carbide magazine. And then we need to go through the clean room patterning process. If we just use magazine as use the as prepared, as pre-coated magazine, we cannot really go through the clean room process because it can be easily peeled off because the magazine is the solution processed. So water can easily go inside. So before we do the patterning, we do a simple vacuum annealing, and then we try to go to use this film to be processed in the clean room patterning. We really achieved a very nice pattern without any peeling off phenomena. And then we think maybe since this magazine is highly conductive, we can use our well-prepared molysulfide as a semiconductor to make a thin film, make a transistor, thin film transistor. So this is the whole process. And finally, this is the magazine thin film sample. This is molysulfide wafer thin film. And this is the molysulfide transferred on the patterned magazine. This is the final device. We can see the nice arrays, they showing very reliable patterning process. So it means magazine is really a good material. This is a demonstration that magazine can really go through the clean room process and then it can be used to make some circuits. So this is the device performance related things. This is a device structure. We use magazine as contact, as the top gated transistor source contact, drain contact, and also top gate. We use molysulfide as a channel and also ALD grown aluminum oxide, hafnium oxide as the bilayer dielectric layer. We found that even though we use the thickness around, we use a dielectric thickness around 8 nanometer, we can still have a good device, have a reliable device performance. This is the representative device device based on the ultra thin dielectric layer. We can see the leakage current is very small, even though the dielectric layer is so thin. Actually, this is amazing because if you review the literatures, you will find that it's almost not possible if we use solution processed solution processed metallic film at the electrode and use such a thin dielectric layer in the transistor. So we also double check the different dielectric layer thickness, and we found that if we use the dielectric layer more than 16 nanometer, we can always achieve a workable transistor, and the device performance is really stable. Vibration is negligible, I would say. Even though we use 8 nanometer, around 80% of the device, they are working very stable. They are working, their performance has a very little vibration. So we were thinking this is very good to make a circuit. So we make some of the circuits. This is one of the representative circuits. We integrate we integrate 4 transistors to make the V-shift NMOS. They also working properly. So finally, we also did some. We also explored the dielectric thin film preparation. Of course, it's not traditional one. As we all know that the traditional dielectric layer is traditional dielectric film usually is silicon oxide, hafnium oxide, aluminum oxide, zirconium oxide. But here we want to try if MOF can be a good dielectric layer film. Dielectric film in the electronics, but our MOF, we use the MOF is the full name of the MOF is metal organic framework. We found we reviewed the previous literature. We found that there is very little research to use MOF in the thin film electronics. The reason is most of the MOF, their thin film cannot reach the electronic grade. But recently in our group, my collaborator, who now is a professor in Shandong University, he used magazine, especially vanadium carbide magazine as a precursor. they can really achieve very very good. They can really synthesize very good morph with ultra thin feature, which is a morph nanosheet. And this morph nanosheet can be made into a suspension state. So this suspension is relatively small. If we is relatively stable. Sorry, if we use methanol as a solvent, it can be very stable, and also the distribution of the nanosheet in this suspension is very uniform. So it means that this suspension can be very promising to make a spin coated morph film. So we use this suspension to make the morph film by spin coating. And actually, this film is very good. I didn't show the real sample morphology here, but it's really very good. And we can get very thin morph film, about 20 nanometer. The surface is also looks very flat and dense. So that's why we use this spin coated morph as the dielectric layer in the molysulfide transistor. But we found that this morph is somehow different from the traditional dielectric layer. You cannot really make a transistor, make a top gate transistor if we use morph. But this morph is very good in terms of ionic conductivity. The proton conductivity inside the morph porous crystals is very good. And so we are thinking, why not we use this morph as ionic dielectric layer, ionic dielectric gate. So that's why we make a side gate molysulfide film. And this transistor actually is not a traditional field effect transistor. It's an electron double layer transistor. It means here is the device schematic. If we apply a positive voltage in the side gate, it will create an electron double layer on the surface of the molysulfide channel. So this electron double layer can effectively attune the resistance of molysulfide. So here is the transistor performance output curve and also transfer curve. So it means it's really working properly if we use morph as the ionic gate. I think this is this is a very different thinking to use morph. This is the first time the morph be introduced in the as a dielectric layer, as an ionic dielectric layer in the EDL transistor. So all the above is about the thin film growth and their application in electronics. I think more research will come soon. So that's all. Thank you for your listening.
Thank you for the wonderful speech, Dr. Zhu.
Thank you.
Can you stop sharing your screen, please?
Okay, no problem.
Yeah, thank you so much. It is open for questions. Yeah, so we assume there are no questions for you as of now. And if there are any questions, please write to your conference manager, and yeah, she will help you reach out to Dr. Zhu. Thank you once again for the wonderful speech, Doctor.